In section 4.8 of the textbook, we learned about antiderivatives. In chapter 5, we're going to work towards drawing a connection between those ideas, those of the antiderivative, and areas under curves. And this might be a very surprising connection to think about at first, but before we can make that connection, we need to learn how to find an area under a function. Say, like this one, y equals 4 minus x squared. I want to find the area under that curve, this red area I have shaded here. Now, in this lesson, we won't actually be able to compute that area, but we will start getting an idea of how to find the approximate area under the curve. And the method we're going to use generalizes nicely so that we could then approximate other areas given other functions. So I want to start off by imagining that I'm going to divide the x-axis up into two intervals, each 1 unit long. So I'm going to divide the x-axis into two subintervals of equal width. Well, I can see that that means each interval will be 2 units long, right? Because I have a total length of 2, so if I divide that into 2 equal parts, each one's 1. And for that width, we typically are going to refer to that as a delta x. And I could always think about calculating delta x as subtracting my endpoints and dividing by the number of subintervals I want. All right, so that's how wide each subinterval is. Now, on each subinterval, I'm going to construct a rectangle. And those rectangles are going to have width of delta x, that 1/2, and a height that actually is going to be given by taking the maximum value of the function on that interval. And height that is equal to the maximum value on the subinterval. And I should say maximum y value on the subinterval. So thinking about that, I need a rectangle that has this as its width and a height that is the maximum y value on the interval. And well, I can see that's really going to come from this left-handed endpoint, right? So here's that rectangle. Okay, and on my next subinterval, I see my width of 1/2, and then the height comes again from this left-hand side. And what I realize is that my function is always going down from left to right, so on any subinterval, the greatest y value would always come from the left-hand side. That's only true for functions that are going down from left to right. What I'm going to do now is I'm going to calculate the area of those two rectangles. I'll add those two areas together and use that as my approximation, because what I see here is my red area is a little bit smaller than the blue area, right? I see where they overhang, but it is an approximation. So, the area will be approximately that sum of rectangle areas. Okay. So, what I need to do now is come back here and calculate the function values. Well, these are easy to calculate, so I'll just create a little table for x and y. I need to know the height of this rectangle, and that's what happens when I plug 0 in for x, so I'll get out a 4 for y. This rectangle's height happens at x equals 1, right? And so I'm going to get 3 out for y. So if I want to calculate the area of these two rectangles, that's always a length times a width, or a width times a height, and so I have 4 times 1 is the area of this rectangle, and here I have 3 times 1. right? And what I really have is a function value, a y value times that delta x. So the sum of these rectangles, well, that's just 4 plus 3 is 7. So here in my first approximation, I would approximate this red area that I had originally drawn here to be about 7 square units. Now, if I was with you in a classroom, I would pause here and say, hey, that's an approximation. We know I'm overestimating because I always chose the maximum value. So what I would ask next is, I still want to overestimate, but how could I make my approximation better? So I'll tell you what, pause the video and see if you can come up with a way to make the approximation better. Don't try to calculate it, but just think about trying to make the approximation better. Okay, there are actually a number of things that you could say to making the approximation better. The one I want to talk about in this video is using more rectangles. So this time, I still want to overestimate the area, but instead of using 2 rectangles, I want to use 4 rectangles of equal width. Still just trying to approximate the area under the curve, y equals 4 minus x squared. So I would start off the same way as last time. I want to divide my x-axis into now 4 subintervals of equal width, and I will call that width delta x. And again, right, I can calculate the length of my whole interval on the x-axis, divide by 4, and each one of my subintervals needs to be 1/2 unit long. So I'm going to pencil in some midpoints here, right? Because I now need a rectangle on this little subinterval and on this one and on this one. And I still want to overestimate, so I still want to choose the height of the rectangle to be the maximum value on each subinterval. So on this first subinterval, I'm still choosing this left-hand endpoint here. And I just continue that throughout the whole interval. And I can see that I'm still overestimating because all of my rectangles overhang, right, the red area, right? They all have a little bit on the outside of the curve. But if I compare my 2 graphs, which not to scale, but this overhangs a lot, they overhang quite a bit, and this just, each one seems to overhang by a little less. And I think I'm a little exaggerated on that last one because my picture's not that great. But let's see if I can calculate this. So the height of these rectangles, again, those come from y values. So let's again fill in a table of values. So I need this rectangle's height, and that happens when x is 0. This rectangle's height, that happens when x is 1/2, and so on. And I don't even need to worry about 2. There's no rectangle over there with that height, right? This last rectangle's height comes from x equals 3/2. And now I just need to calculate a y value by substituting into my original function. And I had already done some of these. And I'm going to use improper fractions here instead of decimals because there's nothing wrong with working with things that are out of 4, right? It's not that bad. You could use the decimals here, but if you are, it's better not to round, right? Carry the 2 decimal places it would work out to. So now we need to calculate the area of all 4 of these rectangles. And let's see if we get a, what we think is a better estimate. So each one of these rectangles has a width of 1/2, and then these are their respective heights. And I've clearly filled that spot in wrong. That was a 4 last time, and it's a 4 this time. This is where I should probably just edit that out, but I'm going to let it in there, right, because we all make mistakes. All right, so the area of this first rectangle, that would be 4 times delta x is 1/2, plus, and again, the y value, the height, 15/4 times that same width, 1/2. They all have width 1/2. The height is 3 for the next rectangle, times that width of 1/2, and my final rectangle has a height of 7/4, still times 1/2. So this is my area approximation now with 4 rectangles of equal width, still trying to think about overestimating. All right, so I want to calculate this, and I've actually done that earlier using my TI-83, and you actually get, so this actually equals 6.25, all right, 6 1/4 square units. Well, both of these are supposed to be overestimates, and since this one goes down, it should be closer to the true area under the curve. Okay, so we've approximated this area twice, both with what we'll call an upper sum. An upper sum is an area approximation constructed by dividing the x-axis into subintervals and constructing rectangles whose height is the maximum function value on that subinterval. Well, the equation we've been dealing with, 4 minus x squared, it's very easy to find those maximums. Now, we do realize that if a function, goes up and down and turns a lot, finding a maximum value over a subinterval might be difficult, but fortunately, we did just study how to find minimums and maximums given a function. Well, this is an upper sum. We've been looking at upper sums. Of course, if you can have an upper sum, you can have a lower sum. And to define lower sum, I'd write all of those same things, except for when I get down here, when I say whose height is the maximum, I say the height is supposed to be the minimum function value on that given subinterval. And so I'd actually like you to pause the video here and go on and write in your notes a definition for lower sum that kind of looks like that one. Okay, so now I want to revisit y equals 4 minus x squared. And I want to find 2 lower sums. So let's write that down a little more formally. Let's find 2 lower sum area approximations. One with 2 rectangles and one with 4 rectangles. And here I'm introducing the variable n, and that's just going to represent the number of rectangles or the number of subintervals on the x-axis. So I want to have 2 lower sums, one with 2 rectangles, one with 4 rectangles. I want to be able to compare those with my upper sums. So for n equals 2, now I take the minimum value to draw my rectangle. And here I get 1 rectangle that's definitely going to underestimate area, right? Because I see that it leaves some of the area I had been shading out. And on this one, the lowest value on the interval that ends between 1 and 2 is y equals 0. And so that's the most boring rectangle in the world to draw. It's not a rectangle, it's just a horizontal line. That will be an easy area to calculate. All right, so this is for my n equals 2 case. Delta x, 2 minus 0 is the whole length all over 2 rectangles. Each rectangle has a width of 1, and yes, I can see that. But this is a calculation that we're going to talk about at the very end of the video to try to make more general. Okay, so plug in an x, get out a y. If I plug in 1, I get out 3, and if I plug in 2, I get out that minimum value of 0. This rectangle has an area of 3 times 1. This has an area of 0 times 1. And again, that's a function value times my delta x. And I would approximate the area then to be 3. Okay, well, if I just look at my estimates with 2 rectangles, what I can tell you, what we can conclude for sure, that's the wrong one. All right, here we go. For 2 rectangles, I know that 7 was an overestimate, and I know that 3 is an underestimate, and that would tell me the true area is between 3 and 7. Not too useful of a range here for the true area, but I know it's a number, and I know it's between 3 and 7 square units. Well, let's find our lower sum for n equals 4. And this time I think I'll come back up here and just reuse this same diagram. This time my delta x is going to be 1/2. Each rectangle will be 1/2 unit long. On each interval, I'm supposed to take the lowest possible y value to form the height of my rectangle. And so again, this last rectangle, just a horizontal line and is real boring. All right, so x's and y's. My first rectangle, that low spot, corresponds to x equals 1/2. That's where I get out 15/4. The next one's height comes at x equals 1, where I get out 3. The next one at 3/2, where I get out 7/4. And that final rectangle comes when x is equal to, and I definitely get out a height of 0. I ran out of room there at the bottom of the board, so I just stuck that one over there. Even though I know it's equal to 0, I want to think about that rectangle when I write out my calculation. So this would tell me the area is approximately. All right, and my first rectangle's height is 15/4 times 1/2 plus 3 times 1/2, right? Because length times width, plus 7/4 times 1/2 plus 0 times 1/2. And then I see 1, 2, 3, 4 rectangles, right? Even though that last one's kind of not really a rectangle. All right, so I grab out my TI-83 and I type all of that in, and I find out that this area approximation is 4.25. And so now, if I go back and I look at my upper sum for n equals 4, I had 6 1/4. So what I know now with more rectangles is that the true area is between 4.25 and 6.25. And what I see is with more rectangles, the lower sum went up and the upper sum goes down. And I hope at this point, we're all thinking, well, to make this approximation even better, we should use even more rectangles, and then the upper sum would go down more and the lower sum would go up more, and we get closer and closer to sandwiching that true area in the middle of a lower and an upper sum. And it's like, okay, well, so I've used 2 rectangles and 4 rectangles. I can, 8, 20, 100 rectangles. And it's like, how do I actually think about finding the true area? And that's where we kind of meet the beginning of the course. The idea will be to take a limit as the number of rectangles n approaches infinity. And that should give us the true area under the curve. And the idea stays the same, that the lower sum and upper sum should keep getting closer and closer with that true area in the middle. As that number of rectangles approaches infinity, we'll get to meet in the middle. All right, well, here at the tail end of the video, let's just think about some of the things we've seen. If I just had a function y equals f of x over an interval between a and b, I could ask these same questions. Right, what's the area under f of x on this interval from a to b? And we could use a similar approach. We could say, let's divide the interval between a and b into n rectangles, or divide the x-axis into n subintervals. So let's divide into n subintervals, where n is just some number. Well, they should all have a width, if I use an equal width anyway. The total length between A and B would be B minus A. To make the rectangles all have the same width that would be equal, I would just calculate that as B minus A over N. And then I'd just figure out whatever that width was, divide up my x-axis. I don't know how many tick marks to put there because I really don't know what N is. And then I could draw rectangles, right? And maybe here I want to think about an upper sum. No reason. I could think about a lower sum or do something else. But for right now, let's just think about an upper sum. So up in this diagram, what I want to do is think about finding the maximum value on each subinterval. So on this subinterval, I think it's something like right there. Right, and so there's some value on the x-axis that corresponds to that point. I'll just call that C1. All right, on this next subinterval, I think the left-hand endpoint is its maximum. But we'll just say its maximum happens at some value C2. And what we'll do is we'll just continue that idea through the whole picture. So I'm just going to draw rectangles, trying to hit the maximum value on each subinterval. Right, and I think I gave myself a pretty easy job. See, on this subinterval, I still think that's the highest point. This one, though, I think it's over here on the right-hand side, though that might be hard to tell. And again, the functions change shape, just trying to always take the maximum function value. Then I'd have to calculate the area of each of those rectangles. Well, each of those rectangles has a width, delta x, and a height that's a function value. And I'm just going to call that f of c sub k, right? Because I have a c1 as c2, right? Some spot I'm using in each subinterval to be the x value for the highest point, right? But the idea is I'm plugging in an x to get a y because each of my heights was a function value. My area approximations would all then have the format f of some c1 times delta x plus the next function value that represents the height times dx plus all the way until I get to the last one. And when I think about the values we've seen in this video, that's what this is. This is a function value. This is f of 0 times delta x. This is f of 1/2 times delta x. Function value times delta x. All the way through for all four. So this notation, this kind of calculation is going to be helpful for us as we go through and learn more about these. In our next video, we're going to revisit y equals 4 minus x squared, and instead of finding an upper sum or a lower sum, we're going to consider what's called the midpoint rule.